Hello, today I'm going to talk about ocean loading flexure and the potential influence on seismicity. Since the last glacial maximum, the eustatic sea level has risen around 120 meters. As the sea level rose, the extra water added a vertical load to the ocean basin, but not to the continents. For the uneven distribution of load, the lithosphere at the coastline flexed about the edge of the load at the shoreline. And this can influence the stress state at the faults along coastlines. Today, I'll talk about the induced stress due to the flex of lithosphere. This slide is showing the stress perturbation from ocean loading. The greatest stress perturbation are within a few hundred kilometers of the coast. A fault within this region could experience up to 1.2 megapascal change in shear stress. Where a tectonic plate boundary falls in line with the coastline, there is the potential for the faults associated with that boundary to be influenced by ocean loading or sea level rise. Features like mid-ocean ridge and deep ocean subduction zone are not affected by ocean loading because the ocean load is uniform there and no bending stress is induced. An onshore transform fault like San Andreas fault or Alpine fault is is potential to experience a large stress perturbation from ocean loading, which is shown in my following slides. This slide is showing ocean loading at the San Andreas fault system. Normal stress is the result for a 120-meter sea level rise on a vertical fault plane striking 50 degrees west of north, which is the main trend of San Andreas fault. The effect of ocean loading on vertical faults is extension, which is positive normal stress, shown by red, onshore, and compression offshore, which is negative normal stress, shown in blue in the figure. These zones of perturbed stress have magnitudes up to 1.5 megapascal and follow the coastline. The thick black line here is the San Andreas fault. Along the strike-slip San Andreas fault, normal stress is about 4 times larger than the shear stress, which is shown in this figure here. And this is the principal component of Coulomb stress. This slide is showing ocean loading at the Alpine fault system. Normal stress is resolved here for the same condition, 120 meter sea level rise, on a vertical plane striking 55 degrees east of north. In general, onshore regions experience an extensional perturbation or positive normal stress, whereas offshore region experience additional compression or negative normal stress. The magnitude of perturbation in this case is up to 2.4 megapascal, which is 60% greater than San Andreas fault. And the reason behind it is the island is being loaded on both sides, and the width of the island allows the bending effects from each coast to overlap. This is another scenario which is showing ocean loading at the Cascadia subduction system. Normal stress is resolved for a 120 meter sea level rise again onto a plane dipping 15 degrees east and striking 5 degrees west of north. Compression or negative normal stress is observed in shallow offshore portion, and the extension or positive normal stress is shown in the down dip fault. However, the normal stress is perturbed by up to only 0.6 megapascal, which is lower compared to the other two scenarios. The reason is here for the lower normal stress perturbation is the shallow dip of the fault. To summarize, the stress tensors due to ocean loading shows perturbation in coastal regions. It is possible that the non-tectonic influence on the seismic cycle could be detected at major plate boundary faults such as San Andreas or the Alpine Fault. However, it's more likely that the influence of plate bending in response to ocean loading would be observable on secondary faults, which is much lower tectonic loading rate. Thank you.